Okay, in this final lecture on lighting and shading, what I'm going to do is look at per vertex and per fragment shading, which are essentially the Garot and the Phong shading that we talked about in the last lecture. And we're going to do this all by looking at the code for doing those, and this code's available on the website for the class. So we're going to do this calculation, which will be the same pretty much if I do it within the application, at least for the per vertex shading. And at the end of this, I'll show you examples with the shaded sphere, with both doing the exact normals that we started with last time for comparison, and then the per vertex and the per fragment shaders. So let's start off with the per vertex shader, where we send over the normals, we do the calculation at each vertex, and then we let the rasterizer pass that information over to the fragment shader, where those are nice, smoothly interpolated between the vertex shades. So here's our little vertex shader, and the fragment shader in this case will turn out to be very simple. So here's the ambient product, the diffuse product, and the specular product that we computed in the application. Showed you last time, and we send those over as uniforms, likewise with the shininess and the position, in this example, of a single light source. Now, since this is really pretty much what we do anyway, we have to send over the position. That's always what we have to do. We're also going to send over the normals for each vertex, and we're going to send over, for this general case, so I'm not restricting the coordinate system, the appropriate model view and projection matrix. So this is a pretty standard bunch of stuff we're going to send over, and the output of this is going to be not only the position in clip coordinates, but we're also going to compute this color that we send on over to the rasterizer. Okay, so let's look at the code now in the main part. Now, here's the big issue that I probably should have discussed more earlier, is where do you actually do the calculation? Not just whether you do it in the shaders, you do it in the application, but also what space do you perform the calculations in. Now, historically, when you had the fixed function pipeline, what was happening was you would specify a normal, and it was automatically transformed into eye coordinates or camera coordinates by the present model view matrix, which are part of the state. Because those things have been deprecated, those functions, you actually can do the calculation wherever you like. You can do the calculation of the light in the object coordinate space, or in the eye coordinate space. There's real arguments for doing it in the eye coordinate space. Otherwise, you can get into problems where it's just not going to look right. The specular reflections won't be in the right place, and also how it then combines with some other things we'll be doing later. So I'm going to do this calculation in eye coordinates. So the first part of the code is converting the position of the light and the position of the viewer into, or the vertex, into eye coordinates. Now remember, in eye coordinates, the origin is where the camera is located. So that's what accounts for the sign change. And what I'm going to do now is compute now in the eye coordinate space where the light vector is pointing, where the viewer is, where the vertex is, which now the vertex has been changed because I've now moved the origin, the origin to where the camera is. And here's the computation of the halfway vector by just adding that transformed light position and the transformed eye position, the transformed position of the vertex into that new space, add them together, normalize them, and that gives me that halfway vector. Now notice too here that we're not applying the projection matrix, because if we apply the projection matrix, that would be converting us into clip coordinates, not eye coordinates, and eye coordinates is where we're trying to do the calculation. Also notice that we're using a selection operator to just take the first three components, because these guys are specified as positions in four-dimensional space. They were points, but I'm now looking at directions that are computed from the origin out to those transformed points, and so I really want to use vec3s here, and we use that selection operator to do that. Okay, I also have to transform the normal. If I transform the position, I also transform the normal. Here I'm arguing that this is really obtained by just the same thing that I did up here, multiplying by the model view matrix and then just selecting those first three components. That's not the most general case. What's happened here, and this is in the book, that the matrix you actually apply here is called the normal matrix, and it used to be maintained in the fixed function pipeline, which is actually the inverse transpose of the model view matrix. But it turns out, in this case, because we're not doing any scaling, it turns out to just be the model view matrix again. So I'm using that over here to simplify the code a bit. But the general case, you'll see what's called a normal matrix computed inside of these shaders or sent over by just as the way the model view matrix is sent over. Okay, now we can compute the three individual terms in the lighting equation. So the ambient product is really simple. I got that by just multiplying those coefficients together in the application and sending them over, so I wouldn't have to send over two things and then just multiply them together. Now I compute the diffuse component. So I need the dot product of L dot N, but I want to take the maximum of that at 0, because if it's less than 0, that says, hey, that surface is pointing away from me, there's no light contribution from there. I don't have any color contribution. So I'm going to take the maximum of that. Then I'm going to multiply that constant, which is actually, I'm going to multiply that constant, which is the same in all three dimensions. It's just that cosine, or 0, and multiply that by the diffuse product that I passed in. I'm going to then do a similar calculation for the specular component. I'm going to compute a constant Ks, which is the cosine raised to the shininess, except if this thing turns out to be negative, I want to do a check on that, so I'm going to do the maximum of that at 0, and then take that to the power of the shininess. Notice how we're using these GLSL functions in here to do all of this work. Then I multiply that by that specular product that I passed in. Again, I want to check whether the surface is not pointing back, whether this is a component that's pointing towards me, not away from me. And if that turns out to be negative, this same dot product, I just set that specular component to 0. I compute the position in clip coordinates as usual as the product of the projection matrix, the model view matrix, times the incoming position. Output that is GL underscore position. And I get the color by adding together those three components that I computed up here and making the fourth component be 1. See, the problem here is that if these three components have values of 1 for the A value, this is going to add them all up and put something not 1 over here. So I'll just set that equal to 1. So anyhow, this is a very basic modified Phong lighting model applied in the vertex shader. Now, what we've done here is, because we've passed on that color, let me come back here, as a varying variable, it's going to be picked up within the fragment shader after it's been interpolated by the rasterizer. So the fragment shader for per vertex lighting turns out to be very simple. It simply takes that color and outputs it. That's it. So it's a pass-through shader on the color, because that's considered to be totally determined by the vertex shader. Now, how do things change if I do that? Want to do the calculation as a Phong shader instead of a Gouraud shader by doing the calculation of the lighting at every single fragment? Well, it's almost the same. What I do is I'm going to send the same information over to the pretty much over to the vertex shader. So you see the position, the normal, the model view matrix, the projection matrix, light position, all being sent over. But notice here that what I'm doing is I'm going to compute the normals at each vertex in object coordinates here and send them out to the fragment shader, because the fragment shader is going to need the normal, the direction to the light source, and the direction to the vertex for each vertex that I process here, that will then be interpolated in the rasterizer. So these are now varying variables, because the computation is actually going to be done in the fragment shader. So Here's all the vertex shader has to do is compute L, E, and N, and so they'll be output. So this is, pretty much exactly the same as what I had in the per vertex shader. The only difference is I don't do the rest of the calculation. I compute the position because I have to, and these things we just defined as varying variables, so they're being passed on to the fragment shader. Now if we look at the fragment shader is the one that's going to take in the ambient product, diffuse product, and specular product, and the shininess, because this is where I do the calculations. It also shows that uniforms can be sent either to the vertex shader or to the fragment shader. Here's the incoming N, L, and E from the rasterizer. And now if you look at the main and the rest of the shader, of the fragment shader, gee, this is pretty much exactly what I had before. Every component is computed in the same way, and now I just output that color as the fragment color. I add up the ambient diffuse terms and set the A component to be 1. So, the code is almost identical. And if I had chosen to do this calculation, and the example is on the website for the sphere, in the application, I'd be computing exactly the same things, but using some of the MVJS functions. But this is the way people do it. I mean, you really want to compute the lighting in either the vertex shader or the fragment shader. Well, here's 2 examples of the teapot to try and show you the difference between per vertex and per fragment shading. This is the per vertex shading here, and here's a little area around the specular highlight blown up. Here's the same thing done by per fragment lighting, and it sort of shows you, I hope you can see that on the video, that this is a much sharper or a little sharper highlight than what you got with per vertex shading. And certainly this will depend some. Also, you can notice, you sort of can notice here that along the spout here, the highlight, and along the handle here, the highlight is going to be much narrower than it is over here when you're doing per vertex shading. So you should be able, depending on your objects and your resolution, to really notice that difference. And it's questionable whether you take much of a performance hit by doing that, because modern GPUs have so much parallelism that you're processing many, many fragments at the same time. So you don't take as much of a hit as you would have taken earlier, when there might have been a GPU that was programmable but would only have one vertex shader and one fragment shader, or just a couple of fragment shaders. Okay, so let me finish this up by looking at some of the examples that are on the web. Let's see if I could get that. Okay, so here's the example. I have 3 versions of the shaded sphere here. The first one, this is the exact normals. This is the recursive subdivision of a tetrahedron, pushing all the subdivided vertices out. The initial subdivision is 3 subdivisions, so you get this kind of smoothness. This radius is changing where the light source is, I believe. If I decrease it, that'll make it brings the light source in closer, so you get a bigger specular highlight, and you see the shading here, which is basically because of the diffuse term. If you want to decrease the number of subdivisions, it's kind of cute. You can see, now you start really seeing that the subdivisions, you can get it actually. Here's the initial case where that's a tetrahedron, you're just not seeing the other parts. I now subdivide once, subdivide twice, subdivide 3 times. Here you can see a little bit of still seeing a little that this isn't quite smooth. And what these 2 buttons do is rotate the object. Now, if this is a sphere, I shouldn't see much difference as I rotate, but in fact, you are seeing differences. And you really shouldn't, but this is because of the sort of chunkiness of the subdivision. If I increase the subdivisions, I hope this turns out right. Let me increase the number of subdivisions. Now when I start rotating it, you're really not seeing any difference, so it's looking much more like a sphere. So that's a test. You can also, if you decrease let me decrease subdivisions again. You start seeing that silhouette edge over here, even though it's smooth. Now, that's doing everything with the exact normals, which works great if you're at every fragment. That works fine if you're if you're a sphere. But in more general cases, you have a polygonal model. So let's go back and look at shaded sphere 2. Yeah. And this one is using per vertex lighting. Let me decrease this a little bit. Decrease it a little more. So again, this is 3 subdivisions to start, and you can go down in subdivisions, down, back like you did before, back up. Now, if you can play with the rotation, and you could see a little bit of changing because it's pretty rough there. If I increase the number of subdivisions, hopefully you're not going to see much change. Yeah, you don't see much change. And then the final one here is sphere 4 is per fragment shading. So let's look at that one. This is per fragment shading. Let me decrease this to change the light a little bit. So now here you can really see the subdivisions here. This is the Murray effect. You see the lines on either side because the resolution here just isn't good enough. So I can increase the subdivisions to sort of smooth that out, and now you can play around with theta, rotating by theta, rotating phi. You don't see a change because I'm not moving the light source, I'm rotating the sphere. So play around with those programs. You probably want to at least start with some of the code in there when you start doing lighting on your own projects. And what we're going to do now is this really sort of finishes up the traditional basics of geometry, modeling, simple polygonal models, how you do viewing, how you do lighting and shading. So the next really major topic is we're going to spend a lot of time on, this will be after the spring break, is all the things you can do with the discrete capabilities of modern systems.